Hello everyone. In the previous lecture we started looking at oscillations in strings. So basically we took a very large number of coupled oscillators, and if it's infinitely large then we can actually describe a string. And we've seen also that we were able to generate a disturbance, and that disturbance was traveling. The mass is not traveling, the movement is in the y direction, but the disturbance is traveling in the x direction. Today we're going to carry on, and we're going to talk about waves, traveling waves and standing waves. And before I start with the analysis, I want to show you two different types of waves. One type which is similar to what we've seen last time. So if you have a string and I generate a disturbance by moving my hand up and down, so in the y direction, and the disturbance is moving in the x direction, that would be a transverse wave, like this one. But you could also think of a spring, a long spring, and you actually generate the disturbance by moving your hand, by pushing the spring in the x direction. And the disturbance is also in the x direction. In that case, this type of waves is called a longitudinal wave. We're going to start with a string. So you have a string here. Let's make some definitions. We have a wavelength of a string, lambda. So lambda would be the distance that is traveled, the distance traveled within one oscillation time. And this wave is traveling at speed v, and it's traveling the plus x direction is this direction. So this is our plus x direction. Alright, we can describe this wave by a sine function. Y of x and t equals a is the amplitude of the wave times sine 2 pi over lambda x minus vt. Now lambda is the wavelength, so I can write it also as the velocity times the period. Now we used to write t for the period, but today we're going to use t for the tension in the string, so I'm going to write p here. Okay, but this is the period. Right? If this is v, the velocity, this has to be the period in order to give the wavelength. And this is v times, the period is 2 pi over omega. So I can also write omega equals 2 pi v over lambda. There's another definition which is called wave number, and the wave number is by definition 2 pi over lambda. Now, if you read in your book French, and note that the definition there for k is 1 over lambda, not 2 pi over lambda. This is how it's been used to define it previously, but it's just a definition, okay? But be careful not to mix things together. If you define k, and this is the more acceptable way of defining it. Now, if you define it as 2 pi over lambda, then you should be consistent with that, and if you define it as 1 over lambda, you should be consistent with that. Okay? We're going to use this definition everywhere. Okay, so now I can rewrite the function y, x, and t as a sine k x minus omega t. There are different ways of writing the this function, and it depends on what really you want to see immediately when you're looking at the function. So this, for example, gives us the frequency and the wave number. You could take the wave number out, which means that you have omega over k here, and that would give you the velocity. So it depends on the application. Sometimes it's more handy to put it in this form, and sometimes in another form, but it doesn't really matter which form you use. All right. So let's keep this form for a while, and what I want to do now is that I want to generate two waves that are opposed to each other, two traveling waves. So this is a traveling wave, and well, just to emphasize the point that I mentioned last time, if you have a wave which is traveling like sine x minus vt, okay, you can think of k out there, but it doesn't matter for what I want to show you. And we say that if there's a minus sign here, and if this is the plus x direction, then this wave is traveling in that direction. I want to make sure that you understand that. Now, imagine that we are following that disturbance by the peak. Okay, so when sine equals 1. Okay, so the peak is at sine equals 1, and we say that this is traveling in the plus x direction, so at time t equals 0, it's found here, but at time larger than 0, it should be found here to the right. Okay, so this is a time larger than 0. Now this is some x here. So at time t0, we have sine x equals 1. Now we're following that peak, so we are only following sine x equals 1, right? Which means that at this time, which is larger than 0, which is x plus some delta x, sine x plus delta x has to be also equal 1. So that Vt has to cancel out the delta x. So basically we need to have a minus delta x here. Right? In other words, that Vt now, which is replacing the delta x here, so sine x Vt, well, v is positive and t is positive, and that delta x is negative, so this has to be negative. Right? And the same thing if it's traveling in the opposite direction, the same analysis holds. Alright, so now let's generate two opposing waves. So we have y1 xt equals, and let's assume they both have the same amplitude, and it's the same type of wave. It's just we generated in opposing directions. Okay, so this is traveling from left to right, and y2 xt a sine kx plus omega t. This is traveling now from right to left. So together, if we superpose them together, we have y, which is y1 plus y2, and that gives is sine A plus sine B if you want. That would give 2 times A sine A plus B, that would give us kx, and cosine this minus this. So this would give us cosine omega t. Now note, what we get now is basically a standing wave. There is no longer this movement. This will be the spatial part, and this would be the temporal part. Okay, so this is time, and this is space. But it's standing, so if you have the peak is here, right? It is moving like that, but the disturbance is no longer moving in the x direction. It remains, the peak remains here, and it's moving up and down. That's what we get. All right. So this is a standing wave. Now let's take an example. So we have a string, let's say that is connected here and here. This is 0, and this is x equals L. What do we know? We know that at x equals 0 and at x equals L, y equals 0, right? It's fixed here and it's fixed here, so it has to be 0 at these 2 points. Kn, for n is for the modes, is n pi over n. Lambda n is 2 pi over Kn, which is 2L over n. And we can write for the frequency omega n, that is Kn times V. This is n pi V over n. If you want to write the frequency in terms of hertz, then we have n times V divided by 2L. Okay, so how is this oscillation looks like for the different modes? For the first mode, it would look like this. So it would go up and down, and it's right. This is the peak. So you see that we need two. This is half of the wavelength, right? And you can see this. You can see this somewhere here. Where is it? The wavelength for the first mode is 2L. The wavelength would be. This is only half, right? There's another half there, and that would give the right. The whole wavelength. Okay, so this is for n equals 1. For n equals 1, we can write L1 is 2L. And we have some omega 1. That's the frequency, or F1. For L equals 2, n equals 2, so now n equals 2. There would be an interesting point here. And you see this is a complete, one complete wavelength. So L2 would be L, and omega 2 now would be exactly, you see this here, omega 2 would be 2 omega 1. This is called first harmonic, and this is called second harmonic. We can do a third one, and it's the same idea. Of course, this would be moving, it is standing. So you can think of each half, so it would be moving like that, right? All right, so this is the first harmonic, and this is the second harmonic, and these points here, all points actually that we have here, so we have 3 points here, this point, and this point, these are called nodes. So we have 2 nodes here also. These are the points where the masses are now moving. Okay, this point is just standing still there. The higher frequency we have, the more nodes we would have. In fact, you can already think of how many nodes either inside or in total. So here would be 1 minus the wave number. So here there are no nodes in the middle. There are 2 on the side. And here we have 1. So the next harmonic, the third harmonic, we would expect to have 2 nodes, and then 3 nodes, and so on. So if you, if for some reason you see a standing wave somewhere, and you calculate the number of modes in the middle, apart from the sides, you know that that is 1 mode higher than the number that you calculated. So in general, we can write also for omega n, and for the Fn is the same here, right? Just for to complete that, F2 would be 2F1. So the frequency of this one would be exactly twice the frequency of the upper one. In this case, we can write omega n in general equals to n times omega 1, or Fn equals n times omega 1. You know the frequency of the lowest mode, the first harmonic, then you know the frequency of all the harmonics. And by the way, this point here, at the maxima and the minima here, and also here, these would be the antinodes. All right, so we can write now in a general form. So in a general form, we write y of n of any mode, x and y, would be equal to some amplitude an sine n pi x over L, and cosine omega n times t. This is the general form of a standing wave. Now, take any linear superposition of such waves and put them together, that would satisfy the wave equation. All right, let's try and make a demonstration here. Let me zoom out here. See if you will be able to see better. change the background a bit. Alright, I'm gonna try and I can't excite the natural modes without actually oscillating this, so I do have to drive the string. Hopefully nothing will break on the other side. Normally I have a student who would kindly help me with the demonstration. You don't want to know what is on the other side. So what I'm gonna do now is slowly try to find the resonance, so starting with the first harmonic and then the second harmonic, and then maybe try to get to higher harmonics. Unfortunately, you won't see the whole picture, but you, if I got higher harmonics, you should start seeing some notes in the middle. Okay, I'm gonna make it as long as possible, so I would be standing somewhere here now. All right, I'm gonna start and look for the first harmonic. I need to just seek for it. I need to find, see at what frequency I should start hitting the resonance. Okay, this would be the, yeah, now I'm on resonance for sure. This would be the, first mode. Let me go to higher modes, it might be more interesting. Yeah, here's a note there. I hope it's actually the camera's capturing that. So there's one note there. That was the second harmonic. I'm gonna try and hit a higher harmonic without breaking the other side. It's gonna be a challenge. Third harmonic. I don't know if you've seen the second note, but definitely one of the notes was about here, and there was a second note on the other side. I'm gonna try even higher harmonic. This is the point where I should stop, otherwise the security will be here soon. Okay, so let's move now to the other type of waves, and for that we can talk about sound waves. Let me zoom in so you can. Okay. So if you think of that spring, I have the spring here, but instead of the spring, we will be talking about sound waves. So think of a tube. Here is the tube. And this tube is, there's air inside. And I put a source of sound inside, somewhere inside. And as a result, there's a sound wave inside. Now, think about the air molecules. They're pushing themselves in the x direction. Okay. just as in the spring example. So this is the tube. Now we can look at the velocity everywhere, so you can have maybe higher velocity here and smaller, and then smaller velocity here. And we can write the something about the displacement in a similar way to what we had before. So I can write in general psi n of x and t is an sine n pi x over L. This is what we had before, omega n times t. But normally when we talk about sound waves, we don't look at the displacement, but we talk about the pressure. You have 1 atmospheric pressure, and at some points you would have higher than 1 atmosphere, and other points you would have lower than 1 atmosphere. And remember now that in the case of the pressure, if you have higher velocity here, higher velocity, you can think about the air particles. They are now more separated. Okay, so you can think of the higher velocity here is associated with the lower pressure. So we can rewrite this in terms of the pressure. Okay, omega n here is the same as before, right? So n pi v divided by L. And before we write this into pressure, v here now is not changing. V is the speed of sound in the tube, speed of sound in air. That would be about 340 meters per second. This is constant now. Now, before we could play with the tension, we could play with the masses, and we could change the velocity of the disturbance. Now the velocity, the speed of sound, is constant in air. So this is constant. So if I'm rewriting this now in terms of pressure, again I'm going to use, I have to use a letter P now, so P now is for the pressure. That would be some amplitude for the pressure times, because as I said before, whatever is the highest displacement is actually the lowest pressure, so this sine would turn into a cosine, n pi x over L, and cosine omega t. And the shape of the pressure for the first mode would look something like this. Oh, this is the tube. So for the first mode, n equals 1, we're looking at the pressure now. We have something like this. This would be this would be a node now, and these two sides would go up and down. But it's the same thing in terms of the wavelength, as you notice. To have one complete wavelength, you need two lengths of this tube. This has a length L, so the wavelength is 2L. So this is just as before. All right. I want to come back now to traveling waves, and obviously there's a disturbance moving, so there is some energy in the system. and I would like to calculate that energy in the system. So we're going to start with the traveling wave. This is y and x. This is traveling with velocity v. Now remember, v is square root of t over mu, and t here is the tension, mu is the mass per unit length. So we can write yx t a sine k x minus vt. It's traveling to that direction. Well, there's nothing really traveling in that direction. No mass is traveling in that direction. The movement, if you remember, is only in the y direction, right? The string can be attached from both sides, right? I just give it a disturbance and it's attached from both sides. And the disturbance is traveling in that direction. But all the movement is really in the y direction. So if there's movement in the y direction, there should be a kinetic energy in the y direction. So we want to calculate this kinetic energy. For that, we can look at a small element here, dx. And for that element, we know the kinetic energy is half mv squared, right? So the kinetic energy for that element, is half mv squared. That's the small element dm, that's the mass of the element, v, the velocity in the y direction. This is not this v here, this is the propagation velocity of the disturbance. The velocity of in the y direction, the movement is in the y direction, squared is half mv squared. This is the kinetic energy. But what is dm? The mass of this small element equals to mu, which is the mass per unit length, times the length of the element, which is dx. So I can rewrite this as half mu dx, and vy squared, I can write it as dy dt squared. Dy dt squared. So I can go back here now, take the derivative with respect to time, and then square the whole thing, and that would be my kinetic energy. So let's do that. So dy dt squared is minus vk, everything is squared, so we can forget about the minus, minus vk a sine kx minus cosine kx minus vt squared. Right, so it would be positive. So now the kinetic energy of that element, only that small element, is half mu dx times v squared k squared a squared cosine squared of kx minus vt. Alright, so we want to calculate the total energy for one wavelength, and that we need to integrate from 0 to lambda. So 0 to lambda, we have 1/2 mu a squared k squared, I'll put it outside, v squared times cosine squared kx minus vt dx. I have everything, yeah. Now remember from last time, a cosine squared, when you integrate over a cosine squared, that gives you half. Integration from 0 to lambda, so this whole thing would give lambda over 2. V squared is t over mu. This is t over mu, and k squared is 2 pi over lambda squared. So let's substitute all these together. We have half mu a squared 4 pi squared over lambda squared t over mu lambda over 2. I lose the 4 here with the 2, another 2 here. This is also cancelled, and we lose 1 lambda here. So we have a squared pi squared t over lambda. So the kinetic energy in one wavelength equals a squared pi squared t over lambda. The energy is proportional to the amplitude squared. If I increase the amplitude of the disturbance by 2, the kinetic energy increases by 4. All right, we can do the same thing for the potential energy, but I'm going to leave this for you to do. Potential energy. Show that what you get is, show that so this is the potential energy, call it U, that U is actually equal to the kinetic energy. So if you derive the potential energy, you should get into the same result here. So now we know the total energy in the system. This is for the traveling wave. So for the traveling wave, the total energy is twice this. So the total energy is 2 times a squared pi squared t over lambda. This is the total energy in a traveling wave. How about the standing wave? Well, one thing you can do, which actually I would like you to do, is derive the same thing. So the kinetic energy and potential energy and the total energy for a standing wave. But I'm going to try now and convince you that the total energy of a standing wave has to be half of this. Okay, and we're going to use the result that we got here. And what is a standing wave of amplitude A? You can generate that by, let me do this up here. You can generate the standing wave using 2 traveling waves, right? But each traveling wave now has the amplitude of A over 2, because when you superpose these, they should give you a maximum amplitude of A. Okay, so now we want to look at energy in standing waves. To generate a standing wave of amplitude A, standing wave with amplitude A, you need two traveling waves with amplitude A over 2 each. So you have A over 2 here, A over 2 here. They move in opposing direction, and as a result we get a standing wave with amplitude A. Okay, so all we need to do now is calculate the energy of these two traveling waves, and that would give us the energy of the standing wave there. What is the energy of a traveling wave with an amplitude of A over 2? You can still see it there. Put this a little bit lower. This is the energy. So the energy of one standing wave would be one traveling wave would be 2 times now A over 2, not A, power 2 pi squared times t divided by lambda. But we have two waves. We have half of the energy comes from this wave and half of the energy comes from that wave to generate that energy. So the total energy for a standing wave it would be twice the energy of one of these traveling waves. We have a 4 here and we have a 2 here, so what we get is half A squared pi squared t. This is the energy. This is the total energy of a single traveling wave. So if we want 2, then I have to multiply this by 2, right? Because the energy goes like the total energy, not the kinetic energy, is twice A squared pi squared, the amplitude squared pi squared times t over lambda, and the amplitude here is A over 2 for one traveling, but we have a second one, so we have 2 times this whole thing. So what we get is A squared pi squared t over lambda, and that is exactly half of the total energy in the case of traveling wave with amplitude A. Alright, I hope this convinces you now. Nevertheless, I would suggest that you make the derivation for a standing wave independently. And you should get that it is half of the energy of a traveling wave. Okay, the last thing I want to discuss here about with relation to the energy. If we have this energy in the system, then I should input some power to the system. I'm just going to give you the result for this is for the power. The average power is 2a squared pi squared t divided by lambda times v over lambda. And that is 2a squared pi squared t v lambda squared. So this is the energy per unit time that we put for one period. All right, so now we go back to the string we're going to talk about the boundary conditions. If I wanted to summarize this module in a few words, then I would say it's all about the wave equation and the boundary conditions. We started talking about boundary conditions, and in the next lectures we are getting a little bit more into details. Now let's take a problem of a string. But this string is made of two parts. One part has the properties mu1 and v1, so the tangent is t. And the other part of the string has also tangent t, otherwise we would have a problem here at this point if we have different tangents. But it has mu2 and v2. So you can think of this part as maybe thicker or thinner, and they are connected together at that point. We generate a disturbance. We can assume that these are long enough, don't need to worry about that. But at some point in time, disturbance is generated and it's traveling from left to right. We call that the incident wave. So here we have a disturbance, and it's coming from left to right, and we call it the incident wave. We give it letter I, and it travels from left to right. And we want to know what is happening for that disturbance. We know the velocity that it's traveling with, and when it comes to that point, the connection point between the two parts of the string, we might expect that something would be reflected back, and we might expect that something would be transmitted to this side. If it was the same mu1 and v1, we would expect it just to pass through without any particular attention to this point. But because the properties here are different, then we think maybe something would be reflected and something would be transmitted. So we can write reflected wave. I'll give it letter R, and I would be moving to the left of this point. And we can have a transmitted wave, let's call it TR, that would be traveling to the right of the x equals 0 and in the plus x direction. Okay. Now let's describe these three waves. For the incident wave, I can type yi equals some amplitude ai, and then sine k wave number. That would be k1 for this side times x minus omega t. The frequency of the wave, whether it's transmitted, reflected, the incidence, it would be the same frequency. We have y reflected, ar sine, same thing, k1, because this is the wave number of this side, which we would expect it to have a different period, a different wavelength, because the compared to the other side, minus omega t. And finally we have y transmitted, a amplitude of the transmitted sine, now k2 x minus omega t. Now we need to know the boundary here, and it's all about the boundary. What's happening at that point? And that gives us the conditions for the boundary here. So we can write the boundary conditions. Let's write this here. Boundary conditions at x equals 0. We know that y1 has to be equal to y2. And dy dx at side 1 has to be equal to dy dx at side 2. Well, wherever the position of this on the right, at that point, on the left, they should be at the same position, so y1 equals to y2, and also the velocity in that direction has to be equal. So these are the boundary conditions. All right. So now we can write what happens at x equal t equals 0. Let's write it here. We get the following conditions on the amplitude AI at x equals 0 and at any time. You can take also time, any time that you want. So at any time that omega t, sine omega t would be 1, also this should hold. That would give us AI plus AR, this is the incident mode plus the reflected mode at that point should be equal to the transmitted mode. This is the first equation. Now we take the derivative now for dy dx, right? And what we get is minus ai times k1, now plus ar times k1 should be equal to minus a transmitted times k2. So now we have two equations and three unknowns. But this doesn't scare us anymore. You can say, well, you just tell me what's the incident mode, what's the amplitude of the incident, and I can tell you the rest. Or in other words, we can solve everything normalized by the amplitude of the incident mode. Using K1 and K2 now, we can write the following: AI minus AR times the velocity V1 equals ATR times V2. Okay. Now we can write the ratio AI over AR over AI, AR over AI, and that if you solve the equations, it gives you V2 minus V1 divided by V1 plus V2, and ATR divided by AI would give you 2 V2 divided by V1 plus V2. Now you can also just call this the reflection factor. Is here the whole thing, and this would be the transmitted factor. If it's not clear how I got from here to here, you can think about the definition of the wave number, right, which is 2 pi over the wavelength. You can write it here. K equals 2 pi over the wavelength. But the wavelength at the start of the lecture, we wrote that is the velocity times the period. Right? So you can substitute lambda in here for one side. That would be with V1, and the period is 2 pi over omega. Okay, so let's see if what we get for what we derived makes sense. So R is, the reflected factor is V2 minus V1 divided by V2 plus V1, and the transmitted factor is 2 V2 divided by V1 plus V2. This is our string, this is the point x equals 0. So this is the part 1 and part 2. And now let's start asking a few questions. What happens if the mass here is infinitely large? So the first case is when mu2 tends to infinity. Put this here. V is square root of t over mu, right? So if mu2 tends to infinity, that gives us V2 has to be equal 0. If V2 equals 0, it means that the transmission factor is 0 and the reflection factor is minus 1. Let's see if we understand this. The meaning of mu2 equals, it goes to infinity, is that you have a wall here. The mass here is so large that you simply have a wall here. So it's just the problem where this part here is fixed at that point. Fixed to a wall. Okay? So mu2 goes to infinity. It's no wonder that there is nothing in that side. There's no transmission. There is a wall here, nothing is moving on that side. So V2 has to be equal to 0. Not only that, but you also get reflection. And that reflection that you got has the same magnitude, but with a minus sign. And that minus sign is actually telling you what we were discussing in the last lecture, that when you're sending a mountain in this direction, so if you send a mountain in this direction, it comes back as a valley. And this is exactly what we get here by solving this. All right. So far, so good. Now let's look at another point where, let's say, V1 is smaller than V2. In other words, the mass per unit length on the left side is larger than the mass per unit length on the right side. What would we expect now to have? If V1 is smaller than V2, V1 is smaller than V2, then R is positive. So R is larger than 1. And also TR is positive. which means that you're sending a mountain now here, and it returns also a mountain. A different amplitude, but it would return a mountain as well. And it would transmit also something, which is also a mountain, because they are both they're both positive. Is this what we expect? Yes, because there is no fixed point now there, right? So this whole thing is free to move up as this disturbance is coming there, is free to move up. So one part carries on as transmitted at a different velocity, and the other one is reflected back. So far so good as well. Now let's take the case where, so here, just to complete these 2 points, the mountain returns into a valley, and here a mountain returns a mountain. Maybe I should write it down. Mountain mountain, and this is mountain to valley. Okay, now let's look at the third example. What happens if V1 is exactly equal to V2? Well, if V1 equals to V2, then mu1 should be equal to mu2. If mu1 is equal to mu2, then there is one string with no differences in the properties. So that there is no actual boundary there, right? So what you would expect to happen is that the disturbance would move from one side to another. There would be no reflection. Let's see if this is what we get. In this case, V1 equals V2. Here we are. Reflection equals 0. So R equals 0. And TR should be equal plus 1. It's 2 over 2. That is plus 1. So you send a mountain and it never comes back. And it remains the same mountain. There is no reflection, and the transmission is plus 1. Okay, now let's take an example where, let's put it here still, trying to squeeze it here, where V1 is twice V2. Or in other words, the mass per unit length on one side is 1/4 of the mass per unit length on the other side. Now, this is interesting because if you substitute here, it's 2V2, that gives us a negative reflection, so R would be minus 1/3, and TR would be plus 2/3. So what happens in this case is that the mountain, write it here, let's just finish with this one, so we have mountain forever, there's no reflection. And for this one now we have a reflection, so have a mountain returns a valley, and is being transmitted as a mountain. This is 1/3 of the amplitude, and this is 2/3 of the amplitude of the incident mode. Now, what happens if we take now the following case where mu2 tends to 0? If mu2 tends to 0, then the velocity here, propagation velocity at this side, would tend to infinity. Now let's substitute. The reflection factor would be equal 1, and the transmitted factor would be 2. Now this is something interesting, and it doesn't make sense at all. You're sending a disturbance, you think in terms of energy. You're putting energy into the system. You get exact energy back. So you're investing in the system, you're putting energy, and you get that energy back. But you get extra energy transmitted. And that doesn't make sense. And this cannot be true. And my question to you is, why is that? And how do we fix this?